Good morning, boys and girls, and welcome back. Today we are going to be talking about power series, okay, and what a power series is. And part one, okay, day one of power series. There'll be a day two tomorrow, but also part one, I believe, is going to be a little bit long. So part one of power series is probably going to be two different videos, so just a quick heads up there. So let's begin. Let's jump into it before we waste any more time. Let's start with, again, our Taylor polynomial approximation for e to the x. E to the x can be approximated using 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on. This is one of those, one of our four that we said we want to have memorized. All right. And as it turns out, it is actually true that, if I wanted to evaluate e of x at any value, if I wanted e of 10 or e of 100, all I've got to do is I've got to plug in 10 or 100 into this polynomial expression. And why I say that, that's exactly, that it happens to be actually true for all values of x is kind of cool, because that's not always the case. Again, we are using these polynomials to approximate these functions, but remember that it doesn't necessarily have to be everything. And let me show you what I mean by this. All right, our friendly little thing here that we used when we first started our Taylor polynomials. Remember we talked about how, as you add more terms, then, it starts to hug a graph. Again, we're using this polynomial to approximate the regular function, and that as we, added more terms, it got to be a better an approximation, okay? This part where it's really close to the graph and is really good, we call that our interval of convergence, okay? Where there it's kind of hugging the graph. And, for some functions, the more terms we add if we go to infinity, I don't know if I can shrink this down a little bit. Maybe show you, as you go to infinity, as you add more terms, it takes up more of the graph. Your interval becomes longer or bigger. But, eventually it kind of dips and dives off, right? But that's what I'm saying with e to the x. It's kind of cool is because with e to the x, as I increase my number of terms to infinity, it actually will equal that entire function the whole way through, okay? And so again, we said, with the interval convergence, some ways around it that we kind of used, going back again with the sine x mainly, and some other ones, is that, if you shifted your center, that would be a way to get it to a, into a spot that you need to do. It moves that interval of convergence around your point of center, right? And so that was one of our workarounds. The other thing I want to show you on this is, for all Taylor series, all power series, this is not true that, if you plug in, it'll be that exact value. For instance, if we look at the graph of 1 over 1 minus x, okay, or 1 plus x squared plus x cubed plus x to the fourth, if we look at that series, as we increase the number of terms, this gets better, but notice how it's not going out in this case, okay? It just kind of goes back up and down, okay? And it never gets to this side of the graph that's over on this part over here, right? It never even touches this one. If I wanted to approximate, if I wanted to approximate 4, I can't plug it in here because it's not going to give me a very good approximation. I would have to shift my center. It's going to let me here. I don't know. I would have to shift my center in that direction. All right, sorry, my computer just had some weird issues and that froze and I couldn't get to work, so I had to reload it here. But again, doesn't matter, just to recap here, it does not matter, how big my n gets. If I add lots and lots of terms, that's not going to, fix things. If I want to get over to 4, I'm going to have to shift my center. And I have to move my center over to that side so that my interval of convergence is around the value that I'm trying to approximate. Okay? So, just wanted to give you kind of a visual picture of what we're going to be talking about today. So going back to our e to the x, it's kind of cool that it actually, I don't have to, if I use the whole entire thing, it's cool that it will actually give me, for any value, it'll match up. This is known as a power series, these four here. Basically, if we have a series, an a sub n, times some x to the n. If you have your x's and your series kind of mixed together, that is known as a power series. Okay, this would be a Maclaurin power series because it's centered at 0, and this is not because it's centered at some other value of c. Okay, that'd just be some other Taylor power series. All right, so a power series can be viewed as a function of x, or viewed the same as our function, where the domain is all the values for where the series converges. Again, we had that part where we talked about, the whole thing. There's not going to be a whole entire interval of convergence. So just where it converges, we can consider that during those domains, those values, we can consider those to be a function of x. And so one of the things we know is that every power series has to converge at that center point. Okay, that's guaranteed. We know every power series converges at C. And we also know that all power series will converge in one of the following ways. First, they might only converge at C, and that's the only place where the power series and the function, have the same values. Or, like I was trying to show on the example at the very beginning, they might converge on a finite interval centered on C. Okay? And this is called the interval of convergence. And if you looked at half the interval, then that's called the radius of convergence. So these are some terms we're going to need to be familiar with. The interval of convergence is, that little chunk where they're the same. And then if you look at half that chunk, that is called the radius of convergence. So that's another way a power series might behave. Or your power series might converge for all real numbers. Okay? So that would be like our e to the x, we said. E to the x, it doesn't matter what I plugged in. I could get the answer. So that power series converges for all real numbers. The 1 over 1 minus x, that one only converges on an interval. Okay? So these are the three different ways that power series might behave as far as convergence goes. All right, so when we have a power series, it might be helpful to know what the interval of convergence is, or where it's going to converge. Is it only at C? Is it on an interval? Is it for all real numbers? And so that's what we're going to talk about today, is finding the interval of convergence and then also the radius of convergence. All right? So this is what a power series would look like. Again, it's when you have x's and the n's together. That is a power series. And if I want to find the interval of convergence for a power series, I'm going to use the ratio test. So again, when we use the ratio test, we take the next term over the first term or the previous term, however you want to kind of look at it. So in this case here, my next term would be 3 times x minus 2 to the n plus 1. The n plus 1 is the next term, over 3 times x minus 2 to the n. That is the previous term, or that term that we are on. And we're going to look at the limit as n goes to infinity. And again, with the ratio test, I want to see when this is going to be less than 1. All right? So the first thing we would do here is I'd want to simplify the inside of that absolute value. So the 3's kill each other off. And then when I divide x minus 2, those bases, I subtract exponents. So I would just get x minus 2 to the first, or x minus 2. And so now I'm going to look when this is going to be less than 1. Okay, so we want just x minus 2. And again, we're taking the limit as n goes to infinity. However, there are no more n's left. So this is going to be less than 1 when just the absolute value of x minus 2 is less than 1. So we're going to want to solve this absolute value equation. And remember, to solve an absolute value equation, you need to set up two cases. Case 1, you just drop your absolute value signs. You want to know when x minus 2 is going to be less than 1. Case 2, you're going to, x minus 2, but you want to know when it's going to be, you have to flip the sign and flip the sign. So greater than negative 1. And now I'm going to solve these two inequalities. And we get x is less than 3 and x is greater than 1. Or 1 is less than x, which is less than 3. And so this gets us on our way to our interval of convergence. I know that this is going to converge for values between 1 and 3. All right? Now, the only other thing I need to do here then is I'm going to have to test my endpoints, because I want to know if I'm going to have to include 1 and 3 in that interval. All right, so to check your endpoints, what you're going to do is you're going to go back up to our original power series, and we're going to plug these values in for the x. So here was our original power series, and now I'm going to want to plug in 1 and 3 for x. So I plug in 1 for the x, and I get that. When I simplify that, I get 3 times negative 1 to the n. And if I start to ask myself, does this series converge? The answer would be no. I know that this is a harmonic series, but it's going to fail the nth term test for convergence. if I write out the first few terms, you'll see that you're going to get 3, -3, 3, -3. And so the limit as n goes to infinity is not going to equal 0. And therefore, this is going to diverge. When you do this, always tell people to, like, why it fails or converges. So again, diverges because it fails the nth term. All right, now I got to check my other endpoint. So again, I'm going to plug in 3, and I get 3 times 1 to the n, which is again just going to be 3 then the whole time. So again, this also fails the nth term test for convergence as well. So both these are going to diverge at the endpoints, so I would not include them on my interval. So in this case, my interval of convergence would be 1 between 1 and 3, okay, is where it's going to converge. And then the radius of convergence, again, is half the interval. Because I'm going from 1 to 3, this interval is too long. 3 minus 1 is 2. And so the radius of convergence would be 1. And that is how we find our interval and radius of convergence. Let's go ahead and try this again. Okay, so here's another power series. We want to see the interval and radius of convergence. So again, we're going to use the ratio test. Okay, and so that's, again, the next term over the current term is the ratio test. Again, we want to, and we know that converges when it's less than 1. All right, so now I'm going to simplify this. And when I do this, I kind of keep it in parts. So like I keep my n part together kind of, and then my, if I've got other stuff together, the x part together. When I divide these fractions here, again, you need to flip and multiply. So that would give me n over n plus 1. And then when I divide the x minus 2 over 3 parts, I would subtract exponents, and I would just get x minus 2 over 3 to the first. All right? So that leaves us with this right here. Now, in this case, we have n's left on the inside. So if I were to evaluate this limit, I would get infinity over infinity, which is technically indeterminate. So I would have to use L'Hopital's. However, when I use L'Hopital's, these would end up going away because the derivatives would just be 1. And so they would cancel, and I'm going to be left with just this piece over here. And I know I'm glossing over that math just a little bit there, how that all is going to work out. But if you get this infinity over infinity, they will just cancel each other out because of L'Hopital's. You don't have to write it out or anything. And then we can just focus on the part that we need to find, which is the x minus 2 over 3 is less than 1. That's the part we want to deal with to find our interval of convergence. So again, I've got to set up my two cases to get rid of the absolute value. And now I'm going to multiply both sides by 3. And then we can add 2 to both sides. And we get x is less than 5 or x is greater than negative 1. Or that our interval is going to be negative 1 is less than x, which is less than 5. All right? Now, again, I need to make sure that whenever you do this, when you find this interval, you have to test endpoints. And you have to show on, like an FRQ, your test of the endpoints. So there's my power series. I'm going to test at x equals negative 1. Plug negative 1 in for the x, and I get that. And when I simplify, I'm going to end up with 1 over n times negative 1 to the n. Now, if I look at this, this is the alternating harmonic. So I know that this is going to converge. So again, make sure you tell people you know what it is and why it converges or diverges. But because this converges, I'm going to go back up to my interval, and that means I need to include the negative 1 on the interval of convergence. Okay, now I can plug in the other endpoint, and I'm going to test at 5. When I simplify this, I'm going to get 1 over n times 1 to the n. And 1 to the n is just 1, so this is the harmonic series. And so this one is going to diverge. So you can tell people what's happening and that you know what's happening. But it's going to converge at negative 1, but diverge at 5. So I need to include negative 1, but not 5. So here is my interval then and radius of convergence. The interval of convergence is from negative 1 to 5, including negative 1, but not 5. And then again, the radius is half the interval. To go from negative 1 to 5 is 6. So if I divide that by 2, my radius is 3. All right, I got a few more problems I got to show you. That'll be on the second part of 9.8a. See you all again in just a hot second, boys and girls.